Now, dear students, let's start chapter 2, exercise 2.1. Two charges 5 into 10 raised to minus 8 coulomb and minus 3 into 10 raised to minus 8 coulomb are located 16 centimeter apart. At what point on the line joining the two charges is the electric potential 0? Take the position at infinity to be 0. Now see here, one charge is positive, another charge is negative. Potential of positive charge will be positive and potential of negative charge will be negative. Now electric potential is a scalar quantity, so no need to think about the direction. So here we will get two positions on the line joining to these two charges where the net potential comes to 0. One position that will be between two charges. So here suppose between these two charges at position P we get net electric potential that is 0. Another position will be on the line joining to these two charges outside it but close to smaller one. Here smaller charge is Q2 minus 3 into 10 raised to minus 8 coulomb. So magnitude wise which one is the smaller one? There you will get the another point. So let's take first point P where we get the net potential of these two charges that is 0. Now electric potential of any charge that is kq by r. Now as per this, the distance of P from charge q1 that is suppose x, then distance between q1 and q2 that is given to you 16 centimeter, so that is 0.16 meter. So distance between P and q2 that is 0.16 minus x. Now at P the potential of q1 plus potential of q2 that is v1 plus v2 1 upon 4 pi epsilon 0 q1 upon r1 plus 1 upon 4 pi epsilon 0 q2 upon r2. Take 1 upon 4 pi epsilon 0 common, take it on right hand side. Now see here, q1 to P the distance r1 is x, q2 to P distance r2 that is 0.16 minus x. So substitute the values of q1, q2, r1, r2 in this equation. So here we will get 5 into 10 raised to minus 8 upon x plus minus 3 into 10 raised to minus 8 upon 0.16 minus x. Now if we take 10 raised to minus 8 common, take it on right hand side, will be cancelled. Then take this term minus 3 upon 0.16 minus x on right hand side, it will be positive. So we will get, then after with cross multiplication, 3x equal to 0.8 minus 5x. Now if we solve it, we will get x equal to 0.1 meter, so that is 10 centimeter. Clear? So here if x equal to 10 centimeter, then from Q2 the distance is 6 centimeter. Now we will get another point, suppose that is R, where the net electric potential is 0. Suppose R is at a distance y from Q1. So Q1 to Q2 that is 0.16. So Q2 to R that will be y minus 0.16. Now as per this one, we can write at position R, R1 that is y meter, R2 that is y minus 0.16 meter. And at R, the electric potential that is again V1 plus V2, 1 upon 4 pi epsilon 0 Q1 upon R1 plus 1 upon 4 pi epsilon 0 Q2 upon R2. And net potential that is equal to 0. Again take 1 upon 4 pi epsilon 0 common, take it on right hand side, will be cancelled. Now substitute here the values of Q1, Q2, R1, R2. So we will get again 5 into 10 raised to minus 8 upon y plus minus 3 into 10 raised to minus 8 upon y minus 0.16. Again take 10 raised to minus 8 common, take it on right hand side, will be cancelled. Then take this second term on right hand side, will be positive. And then after take a cross product and solve it, you will get 5y minus 0.8 equal to 3y. So you will get 2y equal to 0.8. So y that is equal to 0.4 meter. So that is 40 centimeter. So Q1 to R that is 40 centimeter, and therefore Q2 to R that is 40 minus 16 centimeter. Clear to all of you? Now 2.2. A regular hexagon of side 10 centimeter has a charge 5 microcoulomb at each of its vertices. Calculate the potential at the center of the hexagon. Now the given hexagon, that is regular hexagon with side 10 centimeter, it implies that from center each vertices that will be at the same distance 10 centimeter. Okay, so we can say if we want to find the potential at the center, then from each charge the center is at a distance 10 centimeter. Now here total 6 charges are there. For any one charge the potential at the center, that is kq by r, and total number of charges, that is 6. So total electric potential, that is 1 upon 4 pi epsilon 0 n q by r. So here for one charge it is 1 upon 4 pi epsilon 0 q by r. For n charges multiply by n. Now substitute the values. 1 upon 4 pi epsilon 0 that is k, 9 into 10 raised to 9. Number of charges that is 6. Charge that is which value 5 microcoulomb. So 5 into 10 raised to minus 6. R that is 10 centimeter. So that is 0.1 meter. If we solve it, we will get the electric potential at the center, that is 2.7 into 10 raised to 6 volt. Clear? Now 2.3. Two charges 2 microcoulomb and minus 2 microcoulomb are placed at points A and B 6 centimeter apart. A. Identify an equipotential surface of the system. B. What is the direction of the electric field at every point on this surface? Now see here, A and B are separated by 6 centimeter, and at A suppose 2 microcoulomb and at B minus 2 microcoulomb charges are placed. So if we think about the surface which is passing through the center of the line joining to this AB and perpendicular to AB, then at each and every point on that particular surface the potential will be 0. So we can say that is the equipotential surface, because at each and every point theta will be pi by 2. So here equipotential surface is perpendicular to AB passing through the center of the dipole. Now electric field at each and every point that will be perpendicular to this equipotential surface and from positive charge to negative charge means A to B. So direction of electric field at each and every point on the equipotential surface will be from A to B perpendicular to the surface. Clear? Now 2.4. A spherical conductor of radius 12 centimeter has a charge of 1.6 into 10 raised to minus 7 coulomb distributed uniformly on its surface. What is the electric field? A. Inside the sphere. B. Just outside the sphere. C. At a point 18 centimeter of the center of the sphere. Now see here, when the charge is distributed uniformly on the spherical conductor, then charge will be distributed on the surface of it. So if we consider a Gaussian surface which is spherical one very close to the surface of the sphere and just inside it, then net charge enclosed by it will be 0. So flux passing through it will be 0. So we can say inside it the electric field that will be 0. And in chapter number 1 we also discussed this theory, right? Now just outside the sphere. Just outside the sphere means we consider it at the surface of the sphere. So we can take the distance r, that is equal to 12 centimeters, so 0.12 meter. Now the entire charge distributed on the spherical surface that behave like a point charge concentrated at the center. In chapter 1 we discussed this thing. So we can calculate the electric field at the surface, that is E equal to 1 upon 4 pi epsilon 0 q upon r square, that is 1 upon 4 pi epsilon 0 q upon small r square. But in this case small r, that is equal to capital R, that is 12 centimeter. Now substitute the values. 1 upon 4 pi epsilon 0, that is k. So 9 into 10 raised to 9. Q, that is 1.6 into 10 raised to minus 7. R, that is 12 centimeter, so that is 0.12 meter. Now solve this one. So you will get electric field, that is 10 raised to 5 Newton per coulomb. Now see, at a point 18 centimeter from the center of the sphere, it implies that from the center the point is at a distance r equal to 18 centimeter where we want to find the electric field. Now again we can use the same equation E, that is 1 upon 4 pi epsilon 0 q upon r square. Now substitute the values. So 9 into 10 raised to 9, 1.6 into 10 raised to minus 7, r square. Now the distance is 18 centimeter, so 0.18 meter. Square of it. Again solve this one and you will get the answer 4.44 into 10 raised to 4 Newton per coulomb. Clear? Now 2.5. A parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. 1 picofarad, that is 10 raised to minus 12 farad. What will be the capacitance if the distance between the plates is reduced by half and the space between them is filled with a substance of dielectric constant 6. Now we know this thing. If there is air between two plates of the capacitor, then the capacitance C0, that is given to you 8 picofarad, so that is 8 into 10 raised to minus 12 farad. But now the distance is made half and the space between them is filled with substance of dielectric constant 6. So now we have to find new capacitance. So we know this thing, when the dielectric substance of dielectric constant K is introduced between plates, the capacitance becomes K times. So here C0, that is epsilon 0 A by D, that is without dielectric substance and when the distance between plates is D. Now the distance is made half and the dielectric substance is introduced. So we can write Ck, that is K times epsilon 0 A upon distance between two plates. This distance between two plates. But now it is D by 2. So here substitute D by 2. So we can write 2K epsilon 0 A by D. But this epsilon 0 A by D, that is nothing but C0. So we can write Ck by C0, that is 2K epsilon 0 A by D into D upon epsilon 0 A. Or directly here you can substitute C0. So you can write Ck, that is equal to 2K C0. Now here substitute K, that is equal to 6 and C0, that is 8 into 10 raised to minus 12. So 2 into 6 into 8 into 10 raised to minus 12. So you will get new capacitance, that is 96 into 10 raised to minus 12, or we can say that is 96 picofarad. Clear? Now exercise 2.6. Three capacitors, each of capacitance 9 picofarad, are connected in series. A. What is the total capacitance of the combination? B. What is the potential difference across each capacitor if the combination is connected to a 120 volt supply? Now see here, three capacitors are there, each one that is with same value. Capacitance, that is 9 picofarad, so that is 9 into 10 raised to minus 12 farad. Total number of capacitors, that is n equal to 3. Now in series combination, we know this thing, the resultant capacitance, that is given by C1 upon Cs, that is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. And all these three capacitors are with same value. So we can write 3 by C. So we can write Cs equal to C by 3. So as per that, directly we can use this equation Cs equal to C by N. So if we substitute the value here, then 9 into 10 raised to minus 12 upon 3, that is 3 into 10 raised to minus 12, and that is 3 picofarad. Clear? Now B. What is the potential difference across each capacitor in the combination? Okay. Now here total supply voltage, that is 120 volt. So across each capacitor, suppose we consider the potential difference, that is V1, V2 and V3, because in series combination, charge deposited on each capacitor, that is same one. Now here capacitance, that is also same one. So if we consider this potential difference is V1, V2 and V3, then all these three will be also same one. And this V1 plus V2 plus V3, that will be equal to our supply voltage. So here we can write now Q, that is C1 V1 equal to C2 V2 equal to C3 V3. Q is same one, C1 C2 C3 same one. So V1 V2 V3, that will be also same one, and say that is Vc. So we can write now V1 plus V2 plus V3, that is our resultant supply, and that is equal to 3 Vc. So V equal to 3 Vc, V that is 120 volt. So 3 Vc, that is 120. So Vc, that is equal to 40 volt. It implies that potential difference across each capacitor, that is equal to 40 volt. Clear? Now example 2.7. Three capacitors of capacitances 2 picofarad, 3 picofarad and 4 picofarad are connected in parallel. A. What is the total capacitance of the combination? B. Determine the charge on each capacitor if the combination is connected to a 100 volt supply. Now see here, three capacitors are connected in parallel. So values are given to you. One that is with 2 picofarad, second one that is with 3 picofarad, third one that is with 4 picofarad. In parallel combination, the resultant or equivalent capacitance, that is given by C1 plus C2 plus C3. So that is 2 plus 3 plus 4, that is 9 picofarad. Now here we have to determine the charge on each capacitor. We know this thing, in parallel combination, potential difference across each capacitor, that will remain same one, and that is 100 volt supply. Capacitances C1, C2, C3 are different one. Therefore, charge on each capacitor, that will be different one. Now we have the equation Q equal to CV. So we can write Q1, that is C1V, C1 that is 2 into 10 raised to minus 12, into 100 volt supply. So charge on first capacitor Q1 that is 2 into 10 raised to minus 10 coulomb. Similarly, Q2 equal to C2V, C2 that is 3 into 10 raised to minus 12 V100. So charge on second capacitor Q2 that is 3 into 10 raised to minus 10 coulomb. And Q3 that is equal to C3V, that is C3 4 into 10 raised to minus 12 into V100. So 4 into 10 raised to minus 10 coulomb. So charge on third capacitor Q3 that is 4 into 10 raised to minus 10 coulomb. Clear? Now example 2.8. In a parallel plate capacitor with air between the plates, each plate has an area of 6 into 10 raised to minus 3 meter square, and the distance between the plates is 3 millimeter. Calculate the capacitance of the capacitor if this capacitor is connected to a 100 volt supply. What is the charge on each plate of the capacitor? Now, see, we already discussed the theory for a parallel plate capacitor, and we derived the equation for the capacitance of parallel plate capacitor. C0 that is epsilon 0 A by D when there is air between two plates of the capacitor. So here area of the plates that is given to you 6 into 10 raised to minus 3 meter square. Distance between two plates that is 3 millimeter, so that is 3 into 10 raised to minus 3 meter. Epsilon 0 constant always given to you. Here supply voltage that is 100 volt, and we have to calculate the capacitance and charge on each plate of capacitor. So capacitance that is epsilon 0 A by D, substitute the values. Epsilon 0 8.854 into 10 raised to minus 12, A that is 6 into 10 raised to minus 3, D that is 3 into 10 raised to minus 3. Solve it. You will get 17.718 into 10 raised to minus 12, this much farad. Now charge on the capacitor that is Q equal to CV. So substitute the value of C which we calculated 17.7 into 10 raised to minus 12, V that is 100. So we will get 17.7 into 10 raised to minus 10 coulomb. Clear? Now example 2.9. Explain what would happen if in the capacitor given in exercise 2.8, means in previous example, a 3 millimeter thick mica sheet of dielectric constant 6 were inserted between the plates. A. While the voltage supply remains connected, and B. After the supply was disconnected. Now see, here in previous example we calculated the capacitance of the given capacitor, and that is C0 equal to 17.7 picofarad, that is 17.7 into 10 raised to minus 12 farad. If a substance of dielectric constant K is introduced between two plates of the capacitor, the capacitance becomes K times. So now here Ck that will be Kc0, K dielectric constant that is given to you 6. So Ck will be 6C0. Now if this substance, dielectric substance, is introduced while voltage supply remain connected, then voltage will remain constant 1, and charge that will be now Qk equal to Ck into V, because now capacitance is changed, supply is as it is. So Ck that is 6C0, so 6C0 that is 17.7 into 10 raised to minus 12 into supply voltage previously given to you 100 volt, so into 100, so directly here it is written 10 raised to minus 10. If you solve this one, you will get 1.06 into 10 raised to minus 8 coulomb. Now charge on capacitor, that becomes 6 times than the initial one. Now when supply is disconnected, then charge will remain constant. If charge remains constant, then potential difference that will change. Now Q that is equal to Ck into Vk. So Vk that is Q upon Ck. Now Q upon Ck that is Kc0. Clear? Now here Q upon C0, that is our supply voltage, that is 100 volt initially, right? Now when it is disconnected and then after the dielectric substance is introduced, so now the potential difference between plates becomes 1 upon K times, so 100 upon 6, that is 16.7 volt. So here potential difference between plates becomes 1/6. Clear to all of you? Now example 2.10. A 12 picofarad capacitor is connected to a 50 volt battery. How much electrostatic energy is stored in the capacitor? Now capacitance of the capacitor that is given to you, 12 picofarad, that is 12 into 10 raised to minus 2 farad. Supply voltage that is 50 volt. How much energy is stored in it, that we want to calculate. So energy stored in the capacitor, for that we have the equation which we derived in the theory, that is half CV square. So substitute the values. Half C that is 12 into 10 raised to minus 12 into V square, so 50 square. Solve it, you will get 1.5 into 10 raised to minus 8 joule. Clear? Now next 2.11. A 600 picofarad capacitor is charged by a 200 volt supply. It is then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor. How much electrostatic energy is lost in the process? Now see, when capacitor is connected with 200 volt supply, at that time what is the energy stored in it, that we have to calculate first. C1, first capacitor, that is with 600 picofarad, that is 600 into 10 raised to minus 12 farad. Now that is 6 into 10 raised to minus 10 farad. C2 that is also given to you 600 picofarad, so you can write C2 that is also 6 into 10 raised to minus 10 farad. Initially the supply voltage, that is V1 equal to 200 volt. In second case supply is disconnected, so in second case V2 that is 0. Now in first case, when 200 volt supply is connected with the capacitor, the energy stored in it, so that is given by half CV square, or you can write that is Q square by 2C. Okay. Now half CV square, so half C that is 600 into 10 raised to minus 12, or you can write 6 into 10 raised to minus 10 also. V square that is 200 square. If you solve it, you will get 12 into 10 raised to minus 6 joule. Now see here, when supply voltage is disconnected and then another uncharged capacitor is connected, so now potential difference across each capacitor will be changed. So if you want to calculate that one, then it will be lengthy process. So now we will use this equation, Q square by 2C. When both the capacitors are identical one, it implies that the distribution of charge on one capacitor, charge is Q, on another capacitor connected with it, charge is 0. So now distribution of charge will take place. And when both are identical, the charge on each capacitor, that will be half. So Now the situation will be this one. On both capacitor, charge will be Q by 2, Q by 2. Clear? And distribution of charge will continue till the potential difference across each one becomes equal. So now in steady state, you will get charge Q by 2, Q by 2. Capacitance, that is same one. Okay. So energy stored in each capacitor will be now same one. So let's first calculate energy stored in each one. So U1 that is equal to U2, that is, now use this equation, charge square upon 2C. So charge on each one, that is Q by 2 square of it upon 2C. So we can write 1 by 4 Q square upon 2C. But Q square upon 2C, that is initial energy Ui, which we calculated. Substitute it here, Ui upon 4. Now we have to calculate the total energy of the system. So total energy of the system, that is U1 plus U2, that is U final, that is Ui by 4 plus Ui by 4, that is Ui by 2. So loss of energy, that is Ui minus Uf, that is Ui minus Ui by 2, that is Ui by 2. So here 12 into 10 raised to minus 6 by 2, that is 6 into 10 raised to minus 6 joule. So here during the distribution of charge, the energy will be lost in the form of heat. Clear to all of you? Now in this type of cases, there is one equation, using that directly you can calculate the loss of energy, and that is delta U equal to C1 C2 into V1 minus V2 whole square upon 2 into C1 plus C2. Clear? So if you use this equation, then here if we substitute all the values, see C1 6 into 10 raised to minus 10, C2 6 into 10 raised to minus 10, initial voltage 200, then after battery is disconnected, so final voltage V2 that is equal to 0, then upon 2 into C1 plus C2. And if you solve this one, again you will get the same answer. So in entrance exam, to solve the MCQs, directly when this equation is used, then your time will be saved. Clear?